All right, I want to do a quick review as to how to plot some of these things in MATLAB, because in the homework we ask you to use MATLAB to be able to visualize what some of these things look like. So let's say I've got a voltage that looks like what you see here. So this would be an underdamped response where I've got a steady state response of 10, and then I've got this transient response here. So when it's underdamped, I've got an exponential times some cosines and sine terms that give me decaying sines and cosines. Okay. The challenge in plotting something like this in MATLAB is knowing what time vector to use when you're plotting, because remember you're plotting voltage versus time, and to know how to size that time vector, so how long it needs to be, and how sort of finely sampled the points need to be. The other thing that's a little bit challenging, I think, for people to think about in MATLAB sometimes is how I perform multiplications and such. Okay, so just as a quick sort of overview as to the way that works. So in MATLAB, what I'm going to do is I'm going to have things in the vector format, and I'm going to have, let's say, a time vector t, which has a series of numbers in it. So for instance, the way I'm going to set this up is I'm going to have numbers like 0, I don't know, 0.1, 0.2, so on and so forth, all the way out to, I don't know, as an example, 1 second. Okay? So I can have a whole bunch of numbers. And the way I write that in MATLAB is like this. Okay, a time vector has a whole bunch of numbers, and then I put a semicolon there at the end of it. So then what I might do is I might want to define then e to the negative t. So the way I would do that in MATLAB is I would have exp negative t. Okay? Now what that would be is if you looked at that vector, what it would look like is it would have a whole bunch of numbers in it. Okay? So it would have, the first entry would be exp of 0. The next one would be exp of 0.1. The next one would be exp of 0.2. So on and so forth, all the way up to exp of 1. Okay? I'm sorry, I need to be careful about that. They're negatives, right? So negative 0, negative 0.1, negative 0.2, negative 1, like that. Okay? So this would be a vector of numbers, and then cosine of 2 times t, for instance, would be a vector of numbers. That would be cosine of 2 times 0, cosine of 2 times 1, or sorry, 0.1, cosine of 2 times 0.2, and it would go all the way up to cosine of 2 times 1. Okay. If I tell MATLAB to multiply two sets of numbers, let's say I tell it to multiply 2 times 3, well, it knows that that is 6. If I tell it to multiply exp negative t times cosine of 2 times t, MATLAB's going to be very confused about that operation, right? Essentially, what this is MATLAB stands for Matrix Laboratory. So it's meant to deal with matrices, and it deals with multiplications of essentially what we call vectors. The thing we need to be careful of is our goal here is I want to take every entry in this exponential vector, and I want to multiply it by every entry in this cosine vector. That specific operation, so what's happening here is what I call in MATLAB element-wise multiplication. In other words, I want every element in this exponential function to multiply every corresponding element in this cosine function. So in other words, what I want to have happen is I want my result to be exp of 0 times exp of, times cosine of 2 times 0. And I want the next entry to be exp of minus 0.1 times cosine of 0.1 times 2. And I want the next entry to be exp of negative 0.2 times cosine of 2 times 0.2, so on and so forth, all the way up to exp of minus 1 times cosine of 2 times 1. Okay? That's what I want the answer to be. This is what we call element-wise multiplication. Every element in the first vector multiplies its corresponding element in the other vector. So the way we do that in MATLAB is I say I need to multiply exp of minus t times dot multiply cosine 2 times t. Dot multiply, this is what we call element-wise multiplication. All right? If I just simply want to take every element in the exponential vector and multiply it by 10, that just needs to be written as 10 times exp of minus t. That will simply give me 10 times exp of 0, 10 times exp of negative 0.1, 10 times exp of minus 0.2, etc., etc. All right? This here, this operation, gives me this element by element result that I've got here. Okay? So let's look at that in practice for this particular set of numbers. Okay? So I am going to put up here. So I opened up MATLAB, and I already created a vector to do this. So what I mean, you can type these things into the MATLAB command window. Simplest thing to do is I usually write a script. And so what I do is I click, I'll do that slower. So I go to New, and I click on that little arrow going down. I click New Script, and I open up a script. All right, now I've already generated one, and I'm going to copy this over into that script. All right. Now the reason that I do this, I mean, I like the idea of a script because I can just write my commands down and I can go back to them anytime I want to. Right? It kind of helps me to do this. So let's look at how I've set this guy up. I've created what I call a time vector here. All right. Now, how I decided to do this, I'm not going to get into this part right now. We're going to talk about periods of sine waves and things like that. We're going to talk about all that in the coming lectures. I don't want to talk about that. We're going to give you a time vector to use for your plotting. Okay, so in this particular case, what I want to say is this. I've created a time vector, and I have these colons inside my time vector. And what I say is my time vector starts at time 0. It ends at 5 times capital T, which is what I call my period. So it ends at after 5 periods. And the increment between each individual element in this time vector is apparently this much. Okay? So here's what that looks like. So I'm going to do copy. Now I'm going to paste that into my MATLAB window. Okay? And let's look at my T vector. If I just hit T, okay, I see there's 501 elements in my T vector. All right? And I can go through and it tells me each individual one of those T vectors. So if I do, so it tells me what's in each column of that T vector. Okay, so 501 entries. If I do exp of minus T, there's 501 entries in that. If I do cosine of 2 times T, there's 501 entries in that. Okay, so knowing that, let's go back to my script. Okay, all right. So I've defined my time vector. Again, we're going to give that to you guys. Now what I need to do is I want to create this voltage that I've got over in my Word document here. All right, so the way I do that is I say, okay, well, I need 10 minus, now what have I done? I've expanded each of these two terms. I'll center that up a little bit more. I've expanded each of these two terms, this one and this one. So I'm saying that this guy is 10 times exponential minus t times cosine 2t. So that's what I've got here. I have minus 10 times exponential minus t, and then I do this dot multiply with cosine 2 times t. Okay, and then over here I have minus 5, which is from the second term, exponential minus t times sine of 2 times t. Okay? I define that voltage vector. Now what I do is I say, okay, well, I want to open up a new figure, call it figure 1, and I label my axes. I say x label. I want that to be labeled with this time in seconds. Now notice what I did. I had these little tick marks here. Okay, my tick marks tell me what text I can put in. And then I have my y label, which tells me how to make that plot, all right, or how to make that label. All right, so I have my tick mark here, and then I say plot. Basically, I say plot t comma v, where t is basically the time vector that's going to be on the x-axis, and v is the voltage that's going to be on the y-axis. All right. So if I run this thing, if I go to run it, it asks me to save it. All right. So I'm just going to call it Untitled 5, even though that's a silly name. Okay. And I run it. Here's figure 1. Okay. So this looks like an underdamped response, just like we would sort of expect it to look like. All right. Now, if I had an overdamped response, that would be a lot easier. Let's just make this up. I'm going to call this V2. All right. And I'm just going to do 10 times exp minus t. And I'm going to do 5 minus 5 times exp of minus t. Or minus 2 times t, I guess. All right. So if it's overdamped, it has to have 2 distinct and real roots. Okay. So if I did that, and I said, okay, I want to plot that guy, I'm just going to copy and paste this over and say I want to do it in figure 2. I'm going to plot V2 instead, and I run that guy. Oh, there he is. All right. All right. So notice the differences. I mean, I just made that up. This one I didn't have to do any of those funky dot multiplies. Now the other thing I might want to do is, let's say I had a critically damped case. Okay. So a critically damped case might look like 10 times exp minus t. In the critically damped case, I have my 2 roots of my characteristic polynomial being the same. So my answer always has a t times an exponential. So in that case, I would need to do the element-wise multiplication again, and I would say minus 5 times t. Then I do dot multiply exp minus t, right? Because I have to multiply the time vector times exp of minus t times the exponential. Okay, and then I'm going to put that in figure 3. Okay, and there it is. All right. So you get a rough idea as how this idea sort of works. Okay. Hopefully that makes some sense. I mean, the critical thing here, I mean, just to so you guys can see this. Okay, so this is my underdamped example. Needs element-wise multiplication. Then I'm going to say I have my overdamped example. Does not need element-wise multiplication. And then I have my critically damped example, and that does need element-wise multiplication. Okay. All right. So it just gives you a sense as to how to run these. And again, we're going to send you out what time vectors to use, because choosing the time vector, both the increments of time, so this middle piece right here, and the endpoint are a little bit tricky and kind of depend on knowing a little bit more than we've talked about with respect to sine waves, but enough to be able to make some of these plots. And so we'll send you some of that information. So hopefully this helps to do this. And I will share this sort of plot demo with you guys. All right, bye.